x square f0, then plus x this, yes? And find to again we know that A prime acts from this space to the same space. Yes? And what it means, we take this G, yes, from here, and must obtain the double V from here. So the result, A prime G equals to double V, and G capital, double V capital are the functionals. But we know that we have one-to-one correspondence to the function G for the function double V, where G and double V belongs to the space of function of bounded variation with some additional assumption, yes? And so we try to describe again, so as we do, describe the A prime, this operator, in the terms of what happens with the function G small. So we must describe double V small via function G small, yes? So let's try to do it. So A G F, by definition, it is that's all in this. For these functions, that's all, yes? But for another place, by definition of a joint operator, it is just this result. So it is I write this variable to understand by what variable we do. And these two integrals must be the same. So you must understand how it looks like the differential over function W if you know this differential. So let's try to rewrite it in some other terms. Oh, YAB, 0, 1, yes? Every integral from 0 to 1, because space 0, 1. So 0, 1, so change AB on 0, 1. Here, this is a constant, yes? This integral is constant. We can take it outside this integral by variable x. So once more, we must have integration ft with some differential. Again, this is constant. This is constant in respect with the variable t. So I can put this constant inside the integral by t. So sorry, something strange. X square here. And plus but this is 0. So I will write first the picture. And here W. We know that at 0 it must be 0, yes? Okay, then look here, please. We have a value of function at point. So our function W must have jump. What is the value of this jump? This. And then you see that our function begins linear. It's then integral part, but in differential you see that dt multiplied on this constant. Here was x, but you can change here, put x, here x, and inside another letter. So you have a jump, and value of this jump is just x squared dg. And then your function W here inside differential and must have coincide with this differential. So it is linear function with that's t. All this is a constant. Oh, sorry. Here was x in first power, yes? So this is mistaken, so it must be x in first power. And then x squared only for f0. Here x in the first power. So here x in first power. Okay. And then you have a value of f1, yes? With this factor g1. So you have, again, have a jump, and the value of this jump is g1, g of 1. So you can calculate this point. What is the value here? It is in variable t equals to 1. So this is equals to x dg from 0, 1 and variable x plus so it is not correct writing because I don't add the constant. You must add this constant plus this constant c, and this is constant c because you begin your linear function not from the 0 but from this point. And then you have a jump g1, so this is x squared dg plus x dg plus g1. So it is answer of function W in picture. And just now you can write the formula. Equals 0 as t equals to 0. If t belongs to, it equals x squared dg plus t x dg when t belongs to the 0, 1. It linear function on this. I don't write this constant c, but you see this variable t. And then this is analytic answer. That's all. And I remind you that function W and G are continuous to the left only in the interior points. Only in the interior points. So you have the answer. Okay? The fourth?
The commutator is the
Oh, then the operator is so quantum mechanics is difficult science, yes?
Yes.
Because it needs to work with when we began to investigate spectrum. So remind me on this problem. We solve it with help of spectrum, but just now we can solve it only by working with norms. And the main step in this problem to guess a generalization of formula, to modification of formula. So I remind the formulation, this, if commutator equals, so you can modify this formula, you can change the identical on any operator which have bounded invertible, because you can multiplicate it on this and obtain here one.
Can we just say cost?
Yes. So A or B is unbounded. First step, I claim that from this formula you can obtain this formula. How to guess? Try to write what happens when you write squares. So if you take n equals to 1, is it the base? We have a basis of induction. For n equals 1, it just the original formula, yes? So it is base of induction. We prove it with the help of mathematical induction. First, n equals 1, we have this.
Isn't this a derivation of the left, no, this is the right-hand side.
And b powered by n minus pi.
Yeah.
And what is the question?
Isn't this the result of the derivative of b power n?
No. If n equals to 1, we have power 0, so we have identity. By definition, the zero power of any operator is identity. But what is the problem? What is the question? I don't.
How did we obtain this result?
We just prove it. We will just prove it. And how you guess, try to, for example, if you try to obtain this, then you immediately, first step, if you write this, you obtain that it is to be. So, second, let formula true is true for k equals n. Then, third, no, I know that by assumption that a b n equals n b n minus 1 plus b n a. Yes? So I represent this as a b n multiplicated b. And put just, accept this element of this formula. So n b n minus 1 plus b n a multiplicated b minus b n plus 1a. And for these two terms, I put out the brackets b powered n. Here obtain AB, here obtain BA. AB minus BA is identity. This is identity operator, so we obtain our formula for the next n, for n plus 1. So this formula is valid for any n by mathematical induction. Okay? And then I use the triangle inequality, and multiplication inequality. Okay? Is it clear how I obtain it? Then you can divide on this, and you obtain that n equals, not equals, so okay, let's following this. Yes, following this. So we obtain that for any n natural, this multiplication greater or equal n over 2 for any n. So one of this norm is unbounded. So one of these norms is unbounded. Let's start with the new theme, our compact operators. First classical result. So space L2, alpha is bounded sequence, and we define our operator of multiplication sequence. Try to guess the answer. When the operator of multiplication on the sequence is compact. It is bounded if sequence alpha is bounded. And when is compact?
When it's convergent. It's convergent.
To what? To 0. So remind the list of spaces of sequences. It is compact if and only if sequence alpha is from C0. So the limit of alpha is 0. I remind that this means that the limit alpha k equals to 0. This is space of sequences with the 0 limit. So to all tasks for compactness of operator, to solve all tasks, we need to remember the criteria of compact or pre-compactness sets in the certain spaces. Do you remember the criteria of pre-compactness in L2 small or in LP small? Just in L2, work with this operator in L2. Set M lie in L2 is pre-compact if and only if first M is bounded. This is property always must be valid because it must work for the finite dimensional subspaces. In finite dimensional subspaces, pre-compact set is bounded set. And second, all infinite dimensional part must be small. It's in naive language. All infinite dimensional part, dimensional part must be small. It's naive approach. But if you remember it, you can write it more strictly. For any epsilon positive, there exists number n such that for any x from M, the tails uniformly small. The tails of series are uniformly small. So they almost lies in finite dimensional part, in LP and n-dimensional. All finite dimensional parts small by norms, uniformly. Almost finite dimensional. So remember this criteria. So now we can work with this operator. First, by contradiction, for example, it's two ways. You can check this criteria for special subset of unit ball. No. If operator compact, then the image of unit ball must be pre-compact. Yes. For how, for example, you can obtain this. Let's take EK. Basis element. On the cusp place 1 and another coordinates are zeros. Is it from the unit ball in L2? Yes. So is pre-compact. And how looks like these vectors? Operator A acts on cusp basis element. It is 0, 0, 0 on the cusp place alpha k, yes? And use this assumption to this set. If k, it's for any k. So for any element, this must be valid. If I put this inside this S k greater or equal n plus 1, so if k less than n plus 1, all this sum are 0. And if k larger than n plus 1, so we obtain that it is just alpha k less than epsilon. Yes? It means just this. They are all small from place n plus 1. Another approach by contradiction. You can assume that it is not 0, so it is a subsequence which for which you can write inequality from the 0, differs from the 0. Then you again take basis elements just with these numbers of subsequence and check that there are no fundamental subsequences. Is it clear? Another approach to this implication. This implication. So we have a sequence which tends to the zero, converges to the zero. We must check all of these two points. Yes. Let's check first. So we must check that the A the image of unit ball is precompact. So take X from L2 with norm X equal or less than 1. Thickness alpha k is bounded. So we take out the sum supremum. So we obtain that the image of the unit ball is bounded. The image of the unit ball is bounded. A, B, L2, 0, 1 is bounded. And now let's consider the second property. We write this property for just for the tail, for the operator. So we must prove that this sum uniformly small for any x. Yes, up to the convergence. You must write the definition of the convergence alpha k to the 0. For any epsilon, there exists number n that for any k which is larger than n plus 1, alpha k less than epsilon. Yes, it's by definition of the convergence to the 0. Take just this number. We know that all this less than epsilon in absolute values. So it is less than epsilon. And this is less than or equal to 1 because x from the unit ball. So it is less than epsilon. So we prove all two properties from the converging to the 0. So operator of multiplication is compact in L2 or in any LP, but finite. The same for finite P, if and only if alpha converges to the 0, alpha k converges to the 0. Because if you change the power here 2 on P, doesn't change. Only L infinity. L infinity we change the summable norm on the supremum norm. It is another norm, so for L infinity it doesn't work. Question on function of operator of multiplication on function when compact. Again, two situations: Banach situation, continuous function, and L2 situation. L2, we solve this problem with the help of spectrum. It is more easy. But for continuous function, you have criteria, Arcelor-Ascoli criteria. You can obtain it by definition. But let's consider another operator. Is it compact or not? Is it compact or not?
Compact.
Yes, why? For B, you can use theorem. For item B, you can use our theorem, the sufficient condition for of compactness of integral operator. But it does not have, this operator has not form of integral operator. In integral operator, we have fixed limits. But you can write this operator in what way? With some function kxt, and this function kxt, of course, yes, you are right, it is indicator. It is indicator kxt equals 1 if t less than x is 0 if t greater than x. And then we have integration just up to x. And the line t equal x has measure 0, it doesn't change, doesn't influence on the integral. And this is function, of course, lies in L2 0 1 square because it is bounded. It is bounded, and on a bounded domain, it is integrable in any power. In any power. So immediately by theorem we obtain that our operator A is compact in L201. Yes? But if you see, we can't use our theorem for continuous function. Because the assumption of the theorem, the hypothesis of the theorem was that the function kxt must be continuous in two variables. Yes? Theorem 1. And this function is not continuous. It is discontinuous. But you can prove that it is compact directly. Directly. So let f in C01 and norm f equal or less to 1. So we check what happens with the unit ball. Standard methods, put absolute values inside the integral, then this is less than norm, less or equal to 1, and then positive non-negative function, so we can enlarge the interval of integration up to unit. So it is so you have uniform estimation of for any function f, yes? So the image of unit ball is bound, is bounded set. And then you must check equicontinuity. Equicontinuity. Again, the value in some point less or equal to the norm. And I write two absolute value inside and outside integral because I don't know what large x or y. But this estimation is valid. So one by hands you can check that this. So if you want that this will be less than epsilon, you must take delta equal to epsilon. Yes. So take the. And you obtain the equicontinuity. So our operator is compact. And on lecture I said it orally, but now I can in more detail say that function kxt is defined on interval AB. So on this domain lives our function k of xt. So the criteria of compactness of operator. Function kxt must be continuous almost everywhere except finite numbers of continuous curves. This is t, this is x. It must be discontinuous only on finite numbers of continuous curves, xg of t, which are graphics of the continuous functions, graphics. So you see that this function is lies in this class because it's discontinuous on function on the line x equals of t.
Can you repeat the statement?
Operator this in this form for arbitrary function kxt is compact in space of continuous function if and only if function kxt continuous almost everywhere on the square except finite number of continuous curves which are graphics of continuous functions. It's for common knowledge. You need to prove it, and you need maybe formulate it on the exam. It's sufficient what I read at lecture. Okay? And what you can say about shift and right operators? Right and left shift operators and L too small. Are they compact or not? Are this operator compact in L2 or not? The men don't believe, yes, in compactness. You are right. They are not compact.
Because it doesn't span any interval. Because it doesn't span any interval in L2.
All operators, right and left shift and L2 in these spaces. They are not compact. Why? Take in unit ball simple subset. For example, basis. Take standard basis. In L2 small. What happens with this set after shift, right shift? Right shift, all sequences go to the right, and on the first place you give 0. Yes. It is this subset. The numeration begins from 2. Because the first basis element goes to the second, and no element go to the first basis. But is it possible to find the fundamental subsequence from here? Any distance between two different elements equals square root of 2 if k is not L. Yes, so there are not subsequences. Fundamental. And what happens with this system after this? It is the same. It is just the same. So
they go out of the unit sphere, so that's why
yeah,
they are not bounded. They are unbounded.
It's not compact.
Yes. So
Unit sphere is not bound. It's not compact set. It's not compact set.
Well, as we shifted it.
Yeah. And I remind you that these operators are adjoint to each other. And how connect between two properties, adjointness and compactness of operator. The main theorem without proof. A is compact from X, Y if and only if Banach adjoint operator is compact operator in corresponding spaces. The idea of proofs is like Arcelus-Colli theorem for operators. But this is valid in any Banach spaces. For any Banach spaces, XY. XY Banach spaces. But for Hilbert space, the proof not very easy, but not such difficult as in Banach spaces. Let's consider the situation in Hilbert space. It's for any XY Banach spaces. And now let us consider H. So the statement let A is bounded in H is Hilbert space. H is Hilbert space. If A star A is compact, then A is compact. And if A star is compact, who stands on the first place in this composition? Then from compactness of composition we can conclude that it is very interesting statement, very useful. For example, what we can say about self-adjoint operators. If a square of operator is compact and operator is self-adjoint, it is compact due to this statement. But if you take away the assumption of self-adjointness, that is not true. Moreover, you can find operator which with infinite dimensional space, with a finite infinite dimensional space, with infinite rank, with square equals to 0. Zero operator is compact operator. But operator is not zero, it's not compact. But operator is not compact because it is not self-adjoint. For self-adjoint operators, it is impossible by this. So let's solve it, this statement. Is it clear that this is symmetric statements? They are symmetric, but just the changing of operators A and star. So the proof's the same. So we prove only this. We prove only this. So we must check that the image of the unit ball is pre-compact if we want to prove this for operator A. We want it just for operator A. So take sequence in the image of the unit ball. So we work in Hilbert space, it is complete, sufficient to find fundamental subsequence. Yes?
What you wrote here? Pre-compact
Or not pre-compact. Or not pre-compact. Of course, the statement is yes, but we just now we do not know. Yes, we don't know the answer. So take the sequence in the unit ball, in the image of unit ball. By the definition of this image of the unit ball, what you can say about any yk? For any k, there exist xk from the unit ball just such that yk equals to axk. Pre-image. They are from the unit ball. What you can say about this set? What you can say about this set? Maybe not right, just better in such form. What you can say about this set? Looks about statement. A star A is compact operator. Xk from the unit ball. So this set is pre-compact. Is pre-compact. So what you can find? Subsequence. Yes. So they exist. Fundamental. Sub for k subsequence. Let's use these indexes for these elements and check if it gives us a fundamental subsequence here. Understand the idea? Take sequence for our operator, with the help, find the pre-image, use the compact operator, find good indexes. Then ideally take these indexes for this subsequence. I write square. I write square because the square of the norm we can rewrite in form of scalar product without any square roots. I put these operators here by definition of a joint operator. Then use Cauchy-Bunyakovsky inequality. What you can say about each factor? What estimation is valid for this norm? It is less or equal to what? No. 2. They are on unit ball. By triangle inequality, it is a unit ball, so it is less or equal to 2. And what you can say about the first factor? It goes to 0 because it is pre-compact, it is fundamental subsequence. So this is go to 0 as nk and m go to the infinity. So we find fundamental subsequence. So operator is compact. You immediately obtain the equivalence of compactness of operator and Hilbert adjoint operator. So corollary, A is compact in H if and only if A star is compact in H. So if you start to investigate the operator, it may be difficult, but you can find the adjoint operator and investigate a joint operator. And moreover, with all statements which are valid for compact operators, if it's valid for operator A and operator A is compact, they are valid for A star. Will be convenient for us when we start the Fredholm theory. How we can prove it? By the property of compact operator. What do you know about the composition of compact operator and bounded operator? Any composition of compact operator and bounded operator is compact operator. So if A is compact, then I use second line of our statement. Then I understand, I know that it is bounded, A star is bounded, so I obtain that this operator is compact as a composition of compact operator and bounded operator. And by this statement, we immediately obtain that A is compact. If A is compact, A star is compact, I take first line. And by our statement, we immediately obtain that A is compact. So what for again, I repeat the useful convenience or importance of this simple statement. For self-adjoint operator, if any power of operator A is compact, then operator A is compact for self-adjoint. And the equivalence of compactness of operator A and A star. And now who can prove that in the infinite dimensional space, compact operator has no bounded inverse operator? So I write this statement. Is Banach infinite dimensional. A is compact operator. Then there are no bounded from the point of view of spectrum, the zero is always in spectrum of compact operator. See upon properties of compact operators. Three basic theorems: linear combination, composition with bounded, and limit. By contradiction, if exists bounded operator A minus 1, by definition of inverse operator, it is identity. By the property, by composition of compact and bounded, compact, this is compact, this is bounded. This composition is compact. But we know that identity in infinite dimensional space is not compact, because we prove that the unit ball is not precompact set. Let's consider operator of multiplication on function. We consider the operator of multiplication on the sequence, and we know that it is compact if sequence x converges to the 0. And let's consider this operator in it is compact in the space of continuous function if and only if what happens with function phi? Sequence is infinite on this line, yes, on the natural numbers. So it can converge. But functions is given on the interval. It can't converge. What you can say about? No. Answer is more easy. What? We can see it's given. It's given, it is necessary condition because we want that operator works from continuous function to continuous function. So we must multiplicate it on the continuous functions. No, identity unit function, identity constant, is a continuous function, but this operator is not compact because identity operator in infinite dimensional situation is not compact. No.
Yeah, I mean, it has to be like constant.
Yeah, good intuition. I can prove it one side, very simple. The simplest example of compact operator. The simplest example. Answer, zero operator. Zero operator, if you take any arbitrary bounded set, it changes into the zero element. One zero element is precompact, of course. So this is obvious, yes? It's obvious. And another, so let's remember the Arcelor-Ascoli theorem. Again, it's Arcelor-Ascoli theorem. So in this situation, by contradiction, let exist point x0 such that phi x0 is not 0, yes? If function is not identically 0, then exists at least one point for which function is not 0. And moreover, without loss of generality, can we assume that this is positive number? Without loss of generality. So, by continuity of function, what you can construct? Now use the continuity function. It is positive at some point. Have non-zero distance from zero on some subinterval. So, for example, they exist some constant positive that function not less than c on subinterval. If x0 is point B, then we take another side subinterval, yes? Not the right or left neighbor. Consider when x0 is not B. Let's consider that x0 is not B. So we consider right side. And take n such that 1 over n less than this delta. And put function fn of such type. The norm of all this function equals to 1, yes? The maximum. So if operator A is compact, then this set is what type? What you can say about this set? Precompact. is precompact. So it is equicontinuous. It is equicontinuous. What you can say about this difference? Of course, if n is sufficient large, then it is less than delta. So the distance between arguments is less than 1 delta, yes? So the oscillation of function must be small. At point x0, fn equals to 0. So this is 0. This is fn equals to 1. And phi, function phi at this point, on this interval, not less than 1. So it is, what is about equicontinuity? By definition of equicontinuous must be small. If arguments are closed, then the values for all functions must be small. But we can find such n, such that 1 over n is less than delta. Then it is not less, it is not small. It is not small. Yeah? So operator of multiplication on function is compact if and only function is 0. In space L infinity, the answer is the same. But in L2, you can multiplicate it on bounded function, on function from L infinity. So it is almost everywhere 0, up to this sets of 0 measure. So, but in L infinity, it is 0. Yeah. But we prove it with the help of spectrum for space L2 and multiplication on L infinity, because we will know the structure of spectrum of compact operator. And structure of spectrum for multiplication function is not the same as structure for compact operator. So then we obtain the powerful instrument to answer if operator is compact or not with the help of spectrum. Because if operator has no proper structure, then the operator is not compact operator. Okay. So let's something says about inverse operator. Inverse operator, yes? Something on inverse operator. First, again, let's consider this space and operator A of x if this operator has a right inverse, left inverse, or if I take BF equal F prime, yes, then we can see that BA is identity, because the derivative of integral is a function inside integral. So it have left inverse, yes? It have left inverse. Is it have right inverse? If it have right inverse, yes, then we must know that if it exists, what we know about the surjectivity of operator. If we have right inverse, the operator A must be surjective. Yes, we don't know what happens with this operator, but by operator A, we must obtain the whole space. So the range of operator A must be all space, so it is surjective operator. Look on this integral. If function f is continuous, and you take its primitive, what you can say about the range of operator, or image of operator? It function of what class? With continuous derivative. So it is C1, 0, 1, and G at 0 equals to 0. G at 0 equals to 0. So your operator is not injective, or not surjective. The range is not, it is not. Consider operator C with a small norm, You know, the norm of operator C less than 1. Then I state that there exists this operator, and this operator exists too. But it is just by substitution C on minus C. If C have norm less than 1, then minus C has the same norm. So it doesn't matter what signs to consider, but this is more convenient. But then it's if you see an operator as a number, then you can guess to the answer, how to write this. To prove that there exists this inverse operator, the most simplest way is just to construct it. If you construct it and explain why it is bounded, one is bound, so we prove that it exists. So look on this formula and imagine that C is not operator but is number, and the absolute value of number less than 1. Then it is sum of what? Geometric series. So I stated this series is inverse operator to this. Why? First, we must explain why this, when we write in norm space, write the infinite sums, we must check that this sum converges. So consider Sn as partial sum, and then you can write the difference. Let's n less or greater than m, then it is ck, k from m plus 1 to n by triangle inequality. We obtain this estimation, and then by the property of the sum of geometric progression, you can write this estimation. I take inequality here, m plus 1, so first element C norm m plus 1, and divide it on 1 minus norm C. And all this exists because the norm of C is less than 1. What you can say about this difference if we tend m to the infinity? No, I assume that n greater than m, so it is sufficient to tend m to infinity. And the norm of C less than 1. So it tends to the 0 as m tends to infinity. So it is fundamental sequence. So sequence of partial sums is fundamental. What we know about completeness of this space? We have a convenient condition, sufficient condition when the space of operator is complete. Yeah, if Y is complete, then the space of operators is complete, of bounded operators. We consider this operator in Banach space. It is complete, so the space of bounded operators is complete. So it has a limit. So it has a limit. Why it is an invertible operator? Let's calculate this sum. Not sum, but this multiplication. It is, this I find the multiplication of identity on the partial sum. Yes? And then find this multiplication. I change order special. You see that this, and this terms reduced. So it is equal E minus Cn plus 1. And to what operator this operator converge? To the zero operator, because the norm of C is less than 1. This tends to the zero, so this tends to the identity. So this tends to identity. So Cn is a real inverse operator. So it is inverse operator. And what is the answer to this operator? If I change the sign? If you must substitute C on minus C. And when C is in even power, you must write minus. So it is 1 minus C plus C square minus C cube and so on. All even powers change sign. So for small perturbation of identity operator, you can easily find an inverse operator with the help of series. With the help of series. Do you know Hardy operator? Hardy. Hardy operator.
Proof this.
Yes. What is the way to solve item B? How you can prove A is by definition, but with some tricks of integration. And B, how you can solve? By definition, it is difficult. By definition of compactness. But by some property of operators, it's more easier. What additional property of compact operators we prove today? if we take weakly converging sequence, compact operator makes it converging by normal. So we can invent some special weakly converging sequence and check that operator Hardy do not make converging norm. But how to guess for construction of this weakly converging operator? Look at the formula for operator. At what point it is bad? At what point it is bad operator? At what operator can be problems? At zero. At zero. So try to use this idea. Okay. Construct operator with following properties. The square of operator is 0, operator is not compact. Of course it is not self-adjoint, yes? Of course it is not self-adjoint. Operator is given by matrix. In L2 small, operator given by infinite matrix. Infinite to the right and to the down. So AX is coordinate equals as in finite dimensional situation. We find the ith coordinates of the image in the following way, but the sum is infinite. So it is operator in L2. So proof. If the matrix have same property, then operator is compact. Consider operator of differentiation of derivative in space of continuous function. On previous lecture, we discussed the Hellinger-Teplitz theorem. Yes, that if we have unbounded operator, then with symmetric property in Hilbert space, it must have domain. But it is typical not only in Hilbert space. You can the domain of operator I take as C1. So show that right inverse exists. A exists right inverse. Is not unique and maybe not linear. Without A, not unique and possible is not linear. Possible is not linear. We see that in the L2 small for the right shift and left shift, for one of operator, we have not the unique inverse, yes, and maybe not, and here the same situation. And 5. So you make a photo, because I have no, but I have place for 5. I just can put it here. 5. Doesn't matter in what space you consider this operator. You can consider it in A, C01, B in L201. The answer is the same. Find the inverse operator. Find the inverse operator. Not in the series. It is only instrument, the series. Find the finite formula without summation. Okay? You consider this operator is type 1 minus C. You can write it. If the norm C of less than 1, you can write the series. But try to obtain the answer without infinite summation.